Okay, and you probably have received a notification about this. Okay, and I'm going to start sharing my slides. Can everybody see my slides?
Yes.
Thank you. And then I will start the one. Oh, this is in the middle. Okay. Okay. We will keep the questions till the end, since then we can keep the video better for further use. Okay. Okay, so welcome everybody. Like to start with this webinar on programming complex workflows with PyCOMPSs that is hosted by the Center of Excellence in Exascale CFD. Well, a little bit of motivation. We have seen that in the recent years, the EuroHPC joint undertaking have been deploying some supercomputers for exascale supercomputers and also petascales. And in this table, all of them are now on operation, but I've been evolving this table during the last years, coming from tender to under construction and now operational. No? And we have also the next exascale supercomputers, Jupiter in Germany, already being deployed, and also another system in France, okay, which I don't recall the name now, sorry. And we have also Mare Nostrum 5, just a little bit more of information since I come from BSc, okay. It's a system with 4 partitions. We have right now operational general purpose partition and accelerated partition, but there will be 2 other partitions, the next generation general partition and the next generation accelerated partition. And currently has this performance that you can see in the picture. The total performance will be 315 petaflops, okay. So with these large systems, and in general, the large systems evolving, okay, and also the infrastructures becoming more complex with the digital continuum that goes from instruments in the edge, devices in the edge, and new systems like quantum computers and so on in the other side of the spectrum, no? We have a very complex infrastructures where the developers can deploy their applications, no? But also we see that from the side of the application providers, they are able every time or want to develop every time more complex applications to solve more complex problems, no? And in particular, they are interested in being able to combine traditional HPC simulation and modeling with data analytics and artificial intelligence. And in our approach, we are doing this as a single workflow. No? And then we are not only worried about the workflow development, which involve different programming models and different environments, but also to take care of the whole life cycle of the workflow, no? From not only development, but also workflow deployment, how we can make it easier to new HPC users, and workflow operation, no? That goes beyond traditional static workflows, how we can make these workflows more dynamic, and also not taking into account not only the computational aspects, but also data management. No? And in the framework of the flows for HPC project, which already has finished, we work with this definition of the HPC workflows as a service, which takes into account the whole workflow life cycle, no? From the development, deployment, and execution. No? For the development, we're considering workflows composed of 3 different parts. The more computational part that was developed with PyCOMPSs as a Python script, but that could already include invocations to external softwares. And these softwares could be complex simulations or modeling software, but also invocations to AI, artificial intelligence, or machine learning, no? in the same workflow. No? On the other side, we had data pipelines these were described with Apache Arrow pipelines that could describe the data movements between the external the repositories of data to the HPC system. No? And we had then a third component, in this case based on Tosca, that describes the topology of the top-level workflow that involves then these computational aspects and the data aspects. No? After the development of the workflow is stored on a workflow registry to have them available, but also for reuse and further use by other groups of users. No? And we were able to deploy it by the use of containers through a portal that was able to install it in the HPC systems in an autonomous way, okay? And providing then an endpoint that provides like a web service endpoint that could be used by the users to invoke the workflow. No? This was the way of working with HPC workflows as a service. It doesn't mean that we have to work always this way. No? For example, in the CEEC environment, we are directly invoking PyCOMPSs workflows that are run directly inside the HPC system without this endpoint. No? And I would like to talk a little bit more about PyCOMPSs in this seminar. Okay, so PyCOMPSs is a programming environment that provides sequential programming. In this case, we will focus on the binding for Python and parallel execution at the task level. No? And what is a task in PyCOMPSs? Task, it can be a method of an application, of a Python application, that is annotated with this type of decorators, which are the typical way that you annotate code in Python, that indicates that this method is going to become a task in our application. And that then the task is the unit for parallelization. We can run multiple tasks in parallel between them if they don't have data dependencies between them. And then the runtime is able to identify the data dependencies that different tasks have between them, among them, okay? Based on additional annotations in the decorator. In this case, the parameter C is an in-out, so this will be taken into account by the runtime to identify other tasks that can be reading this data. The tasks in PyCOMPSs can be coarse-grained tasks, or invocations to external methods, like, as I say, like MPI applications or even web services, but can be also sequential tasks. So we can have very heterogeneous type of tasks in our workflow. And also offers a shared memory illusion in a distributed system, and in such a way that an application can address larger data sets than the storage space. This is due to the fact that when we have data in memory, we only have data in memory that needs to be operated by the tasks, no? But we can have data serialized in the disk that can be used by the application at other moments. In general, PyCOMPSs applications are agnostic of the computing platform, can be executed in clusters, clouds, and clusters managed by container systems. I will provide a few more slides about the syntax of PyCOMPSs. The basic annotation is this task that I was mentioning before already. In this case, for each of the parameters, in principle, you should have to add the directionality of the parameter. It means if it's read, it will be an input parameter. If it's written, an output parameter, or in this case, for example, the parameter C, if we say that is in-out, means that is read and written by the task at the same time. If we don't say anything about A and B, it's because they are, by default, if we don't say anything, is that they are inputs. No? So in this case, for example, we can have this main program that invokes in a set of nested loops, this method multiply. So at execution time, we will be uploading multiple of these multiply methods that will be identified as tasks. And then the runtime will find out these data dependencies based on the C parameter, because some of these tasks are reading the result of the previous operation, no? And then we have a data dependence between them. But we can see that with some of them that are not using the same block of the matrix C, we have possible parallelism. No? So it's a type of task where we can see that there is the parallelism in the number of blocks of C, but at the same time, we have some data dependencies. No? One aspect I wanted to mention here is that A, B, and C here in the task are not integers. These are blocks of the matrix A. So matrix A, B, and C are block matrices, no? And in this case, A, B, and C are NumPy blocks that are operated by the method multiply. So it's not just a multiplication of two integers, but the multiplications of two blocks. No? In principle, in PyCOMPSs, you don't need to add synchronizations to read data or to wait for a given number of tasks to finish, unless you want to do something special. No? For example, in this case, I have some invocations to tasks, but at a given point, I want to check the value of A, which is generated by a task. No? Imagine A is the output of a task that does a computation on the value B. And then we want to check its value. Since this is going to be done by the main program, it does not have access to the data where it has been generated, which can be in another node. And also, at a given point that we want to check this value, we are not sure if the data has been generated or not. That we need to add this comes wait on here to make sure that we wait for the task that generates the value A to finish, and also to synchronize the data in the main program. We have also this comps barrier, which is useful, for example, when you want to measure time, which will wait for all the tasks that have been offloaded to be finished before continuing with the next sentence in the code. We have also the decorator of constraints, to define constraints. This is very useful to define some software or hardware constraints that are requirements that the task may have. No? Imagine that, for example, we have a task that requires a number of cores to be executed. For example, this computing units equals 8 means that we need 8 cores to execute this task, or if we need a given amount of memory. So we can define this constraint on the amount of memory that this task needs. And then the runtime is make sure that these constraints are respected. No? And this supports also for the heterogeneity of the devices in the platform. No? If it's even in the case of homogeneous clusters, it's useful to define these constraints of number of cores or memory. But in general, if we have heterogeneous platforms with different type of nodes, we can select where the tasks can be run. No? If they need a GPU, for example, we can define so as well. We have been also extending PyCOMPSs to be able to integrate with other programming models. No? So PyCOMPSs can be used as a standalone, only with pure Python code on a whole application in Python, but we can combine it with other programming models. These programming models can be, for example, invoking an external MPI application, or invoking an OMPSS application, or in general, if we have a workflow that invokes external binaries, we can use that binary annotation to invoke external binaries. This, for example, has shown to be very useful with our users from life science that typically have pipelines that invoke external scripts or external binaries. And then PyCOMPSs is used as the code that codifies the main structure of the pipeline. And with MPI, it's used, for example, when we want to have in the same workflow invocation to multiple invocations to MPI simulations or modeling software, like for doing a campaign of simulations, and then gathering the results for doing some AI training or some data analysis. I will show an example of this, for example, with the Calestis project. All of these decorators can be combined with a constraint on, well, with implement that I have not explained it, but it's another decorator that is available. In general, the different decorators can be combined between them. Okay? In particular, I'm showing in this slide how we support MPI tasks. So this means that in a Python code, in a PyCOMPSs code, you can have an invocation to one or more MPI simulations. No? And in general, these Python MPI applications, are not in Python. Typically can be in Fortran or C. No? So we invoke them using Python as a wrapper to invoke the external binary. But in this case, we are adding more information because we are not only saying create this wrapper, we are also saying, okay, use this MPI, this runner for running this MPI, the number of processes that we want to run, for example, or in particular, we can also say the number of processes that we want per node. No? There are other parameters that I'm not showing here, but the good thing is that then with this information available, the PyCOMPSs is able to invoke these MPIs automatically and allocating the nodes to run this MPI simulation inside the workflow. No? We have also support for MPMD applications. So, for example, when you want to have in the same workflow also invocations to external MPI binaries that are coupled between them. It's a similar idea to the previous one, but in this case with invoking more than one MPI simulation. For example, this is an example from the Flows for HPC project where we were coupling the FESOM, which is an ocean model, with this other MPI application, RMFPMA, for example. Okay, and for each of them, you can specify the number of processes that you want to use, and so on. And similar to the previous case, PyCOMPSs is able to invoke this couple execution and allocating the nodes where to run these two simulations at the same time. We support containers in two ways. Here I'm showing that tasks can be in containers, so you can have that a given binary or code is already in a container, so you can invoke it directly from PyCOMPSs without having to manage by hand this container, or it can create a container. But also a whole, I don't have the slide for this, but another way is that the whole application of PyCOMPSs can be in a container, and you can deploy it, for example, in a supercomputer using Singularity, and PyCOMPSs can be executed then deploying the number of containers that you want to use in the location and starting the application from the container. So both things are supported. We have also another interface that I will be showing in an example is the support for data streams. In the previous examples that I've been showing, the data in the methods were like integers or blocks, whatever. No? In this case, a stream would represent a data that is coming along the time. No? That, for example, the images that you receive from a camera, or for example, imagine that you have an MPI application and every X iterations you write a data in a channel that can be read by another one. Okay, so you can have methods that are writing in a stream and methods that can be reading from this stream. No? This task typically will be active until until this channel is closed. Okay, so it's kind of, we call them sometimes persistent tasks, no, because they are active until the end of that channel is closed. No, to differentiate them from the other tasks that receive a number of parameters, do an operation, regenerates the output, and finish. No. Another aspect that is interesting in general is the failure management at task level. Okay, so we have an interface that where you can define the task can have a failure and what to do in case of this failure. No, it can be that you ignore the failure and continue the execution of the workflow, or you can define that the whole workflow fails, or you can just decide that you want to ignore the failure of this task, but also cancel the successors of this task, no? Because this task can have other successors that depend on its result. So you can decide, okay, if this task fails, also cancel its successors, or you can say, okay, retry this task. No? So we have a set of policies that can be used, and then this defines like a more dynamic execution of this workflow, no? that can go beyond the actual static workflow that is defined at the beginning. Because in combination with other strategies, you can define with the failure of this task, for example, like branch unbound structures or things like this. No, if you make in purpose to fail a task and to cancel all its successors, you can define this inside a branch unbound structure of an application, to prune some branches that you want to cancel. No? As an example, we have been using this, for example, in a random forest estimator that we have in a machine learning library. We support also timeouts, so you can say for a given task, okay, if it lasts more than 200 minutes, cancel this task. And you can also raise exceptions. In this case, are COMPSs exceptions, no? So exceptions that can be identified by the runtime. And then we can program some behavior in case of these exceptions. This combined with the construction of task group, which puts multiple tasks in a group, for example, can be used to cancel the whole execution of a set of tasks. Okay, and then after this cancellation of a set of tasks, you can, for example, launch other tasks that are only invoked in the case of this exception. No? So again, it's another case where we can use PyCOMPSs to program workflows that have some dynamicity, no? Some autonomous behavior depending on events that can be internal events because had happened internally in the computation, or external events if you're using the stream interface. You can be receiving information from outside the outside world and decide to do new computations or cancel given computations that are ongoing, depending on these events. We also have a task level checkpointing that supports the re-execution of a failed workflow. Of course, checkpoints have some overhead, but there is a trade-off between the performance and the time to recover. No? And establishing the right checkpoint granularity is important. We did a study and we saw that depending on the type of application, using a given policy on another can be better for each case. No? Then we have, for example, one of the policies is just to do a periodical checkpoint every X time. No? Or it can be based on finishing a number of tasks. You can say, okay, ask the COMPSs runtime to do the checkpoint when it has finished 10 tasks, for example. Or you can define task groups and then do the checkpoint after this group has finished, which it's a little bit different to the finished task because in COMPSs, tasks are executed without order, depending on the data dependencies. So the instantiation of groups doesn't mean that this group is going to be executed one after the task one after the other. No? And also, in case the user wants to implement its own policy, we provide a call to an API that requests COMPSs to perform a snapshot at a given point. Yeah? So how this works, you program you execute the workflow running with this checkpoint and the policy that you specify, and this records the checkpoint. In case of failure, you can then restart the application, and then COMPSs will not restart from the beginning, will restart from the last checkpoint. In general, the PyCOMPSs applications are executed with its runtime, okay, which executes the applications in a distributed mode, following a master worker paradigm. In particular, in supercomputers like in Mare Nostrum, where we have the code already installed and ready to use, we deployed them as an allocation in the job scheduler. So we submit the whole application as a job taking a number of nodes, like say 10, 20, 100 nodes. And then the COMPSs runtime manages these nodes as if it was a standalone infrastructure. Typically, we were using one node before for the master and the main application, but nowadays the nodes are so big, usually we have also a worker in a node that is acting as the master. Okay, so we use also the cores in the master node as a worker in a master. And then, well, basically the application starts in this master node, starts the Python script, starts generating the task, and then the runtime performs the different activities like analysis of the task, no, for finding these data dependencies, deciding where to execute the task, because depending on the constraints, if it's an heterogeneous system, or depending on the policy, because also we have policies for the scheduling, like some policies try to schedule as fast as possible, others take into account the data locality. We are planning to do a scheduling based on the energy consumption, for example. And then also the runtime takes care of the data movements if needed. If you want to run, in the case of Mare Nostrum, we have GPFS, for example, as a shared file system, and we don't need to move the files, then you can leverage this. Or you can also decide to use the local storage in the nodes that typically is available in the clusters, and use these local Ts for storing the temporal data. Okay, and then in this case you need to do data movements between nodes. No? So all this is managed by the runtime. No? Okay, yes, I think this is all in this slide. And then I have, well, this was an overview, and then I want to cover some examples. Okay, some examples come from the CEEC project, no, from CEEC project. In this case, are a couple of workflows that we have been working with our colleagues from the group of Oriol Lemku, and they are based, both of them, on the SOT2D software, which is spectral high order code to solve the partial differential equations. This is a code written in Fortran, has been ported to GPUs, and it's well, has its own GitHub, and it's open source. And one thing is that it's very scalable. No? You have here a chart of the scalability of this code in Mare Nostrum 5, okay, where we can see that it scales very well up to 2,000, more than 2,000 GPUs. No? So in CEEC, they are working in this challenge, no, to research automatic ways to control the aerodynamic performance of aircrafts using under dynamic extreme events. No, in cases where you have nowadays, you have probably heard about it. No, that there are very big bags of air with different pressure. No, that makes very sudden changes in the planes. No, I remember an event that happened with the Lufthansa flight that was a little bit scary. Fortunately, it was not that bad, but it's really, it can be a big impact in a flight. No, so the idea would be to have new tools in the future that can avoid these big movements of the plane. No, so it can react faster to these events. No, so in this case, they are coupling the SOT2D software with a reinforcement learning model using a multi-environment approach to accelerate the training. No? In this case, for example, they are using different environments to train the model. Okay, so in this case, we have the simulation running in the GPUs, and then we have also the reinforcement learning models, multiple models that are trained at the time. And in each case, we have the environments that are sending its state and the reward writing it into a database, and then the reinforcement learning reads this state and reward and returns actions to the jets of the wing of the airplane of the plane to react according to them. No? And well, this is the final idea. No, right now they have a prototype type. They started working on a prototype working with SimGrid and Redis, but we are porting it to PyCOMPSs and Ecuba. No? PyCOMPSs I've already described it. Ecuba is a key value distributed database based on Cassandra, which supports the storage of persistent data without, I mean, it can record data that is in memory in persistent storage, no, within this Cassandra database. So basically what we have is the reinforcement learning and the master of the workflow running on a node in general purpose processors, and then the different simulations of the SOT2D running in nodes, each of them running its own simulation. No? And we have programmed them, the simulations, as PyCOMPSs MPI processes. That can then run in parallel between them and orchestrated through PyCOMPSs. But then instead of writing the data with Redis, now we are using Ecuba to write the results into the Ecuba database in such a way that then the reinforcement learning can read from this Ecuba to generate then the corresponding actions and send them to the MPI. No? You can see the difference in the code, where before we had different lines of code that had to wait for new actions. In this case, the Cuba hides this synchronization and runs it internally. It's able to wait internally for the new data to be available. Another example that we are working is for having at the same time the simulation of the SOT.2D processes and a post-processing to generate a visualization. In this case, this post-process includes the computation of velocity gradients, computation of a second invariant, and also computation of isocontours of Q that I have to admit that I don't know what is this, and interpolate the velocity to the isocontours. No? For this, we run the different CFD simulations similarly to the previous case using PyCOMPSs, and now we use the stream interface that I was showing before to communicate when a partial result has been finished, and then is saved in disk, and PyCOMPSs is able then to launch another task that post-processes the results file in concurrently to the simulation of the simulation that is ongoing. No? This is how it looks. Okay, we have the MPI processes that, as you see, similar to before, they are annotated with that MPI annotation, and in this case, you see that they are writing in this channel FDS that every X iterations is writing some results in this stream. Then we have also the visualization. In this case, is not reading directly from this stream, but we have the main program below. That is the one that is polling the output of the MPI, and then in the case of a new file available, it generates a new visualization. For each of the files, invokes one visualization task that performs the post-processing and generates the visualization at the end. I'm now going to move into another project. In this case is the Calestis project that is also about aircraft, but in this case about the manufacturing of aircraft. No? We are working in another project with aircraft manufacturing industry to develop some projects, to develop some workflows that helps on the manufacturing of some pieces of the aircraft, in particular some pieces of the turbine. No? And we have designed this ecosystem that enables both to run parts of the workflows in external software, because in these cases it's people, engineers that are used to do some of these structures in external software that runs with Microsoft, for example. But sometimes they need to run some simulations in HPC systems. No? So now we have a whole tool chain that enables them to run both in external servers, but also to offload workflows in the HPC systems from a portal, and data is moved automatically with this service from the storage service to the HPC systems and back to the storage service. And in the final stage, for example, in cases that we are training a machine learning model, they can deploy this model in the factory to be able to monitor the manufacturing of species and to enable early detection of defects in pieces or failures in the pieces to enable to improve the manufacturing processes. In particular, we have been working with them with the concept of workflow templates, no? That are templates developed on top of PyCOMPSs, but a higher level. No? What is a workflow template? This is an example where we are doing, for example, some simulations, a campaign of simulations. For each of the simulations, we have a set of input data, and then we prepare the input, perform the simulation, and do some extraction of the results in order to train a model afterwards. In this case, a machine learning model that is trained after, no? For example. This will be the workflow template for the model training here that I'm specifying, but we have other templates available for sensitivity analysis, for uncertainty quantification, or for Monte Carlo simulation. Basically, we have these templates that then can be customized for each of the model. No? So this is like a DSL that then you can integrate with this by specifying the different pieces here, different Lego pieces, you can customize for your actual workflow that you want to execute. Here is a little bit of the code. No, basically the template is a Python script that invokes these phases. No, invokes in this case a sampler here, for example, and then we have a for loop that for each of the data in the input data set, it invokes the prepare data phase, the simulation phase, post-process, and so on. No? And then we have that for each of these phases, we can provide an ad hoc implementation depending on the workflow that you want to do. No? So we have also worked with them to prepare these different phases. No? Here for the ALIA simulator, for example, we have this phase that will invoke the simulation phase. And then this piece can be exchanged, no? For the different workflow templates. We can use the piece if there is a simulation phase in each of them. No? And this is very easy to exchange between them. Or for example, for prepare data, this is an example for ALIA as well, no? For the prepare data for ALIA, no? In this case, it's a Python code that then invokes two tasks, the prepare SLD or the prepare FIE. So depending on the cases, you will have that is directly a task. In other cases, it can be a Python script that invokes tasks, no? So internally it's parallelized with PyCOMPSs. But in the top level, the user don't need to know about PyCOMPSs. It only needs to know about the phases that they want to execute and the type of workflow that they want to execute. And then it can customize the workflow through a YAML file where they specify which workflow type they want to execute, for the different phases, which phases they want to use, and the parameters that need to be used. So depending on the case, you need to provide some parameters or others. And with this, the actual workflow that is executed is instantiated, no? In a very quite easy way. No? For example, we have been using it in this example, which is evaluates an open hole tension in a specimen. No? Imagine you have a piece of material, no? Where you have a hole. No? And in this case, they want to build a model that is able to predict for a given force if the material will break or not. No? So to build this model, they use this model training, but in this case is already the particular case using ALIA, for example. No? They use PyDo, which is a Python module that is able to generate input data given some variables, and you can specify the distribution for which you want to generate the data. So this will be the data in each of the rows is used for a simulation. No? Then in this case for ALIA, we could configure the phases to define how to generate the mesh, how to do the simulation, and so on. And then we were parsing some of the results for each of the simulations to build the training data set. In this case, we have the input data plus the outputs of the simulators sessions are the whole data set that is used to train a model. In this case, we are using the grid search from the DSLib. The DSLib is a machine learning library parallelized with PyCOMPSs. And we can define this grid search that in this case is, for example, training, not say, I thought was say the model. Okay, it's using, I know it's training a tree-based model. I thought was said in the slides. But in this case, it's using the grid set to evaluate different parameters in order to select the best parameters for the model and train the model, which is then obtained at the end. No? And this can be run, for example, then in Mare Nostrum 5 or in other supercomputers where it has all this installed. No? Okay, so I'm going to finish the webinar, no, with some final thoughts. So we see that the growth of these HP systems is ongoing. No, it doesn't seem that it's going to stop. Even we are already building very large systems. So the users need some help to build complex applications. No, and one way to do this is through workflows that can combine different aspects like HPC, traditional HPC simulation and modeling plus AI. But also we see that in the future We will have other type of hybrid workflows like combining classical computation and quantum, or even deployed in the digital continuum, no? That can may use of external components, reading data from instruments, and running part of the computation outside, for example. And PyCOMPSs is a programming environment that supports this type of hybrid executions, okay? And especially it's good to support the coupling of HPC plus AI or visualization, as we have seen with some examples, or also it supports, in this case, I have not been showing any example that show this possibility of changing the behavior, but we have examples where we have demonstrating this possibility of having workflows that have dynamic changes due to changes in internal data or external data that can come from the environment. You can find information about the PyCOMPs in our project page, but also all the code is open source and available. And we have also Docker images that can be used like for testing in your laptop and some sample applications. Also, if you are interested, there will be a longer training in Barcelona. It's a 2 days training in 4 and 5 of February. I can send information about this seminar. Everybody is welcome. The seminar is free of charge, but if you want to come to Barcelona, you will need to take care of your travel expenses, okay, or charge the project if it's you are in a CEEC member or another project that can fund your travel. In principle, I think we will be offering as well as online seminar, although of course attending a 2 days training online is a little bit tough, I think. And well, here, besides CEEC, we are involved in other projects that I would like also to acknowledge. For example, Calestis, that is examples that I was showing, okay? And that's all from my side. I don't know if there are questions.